notes, we are looking at characteristics and important things that we need to know about polynomials. So a polynomial function is of this form: f of x equals a something in terms of your coefficients. These a's represent your coefficients, and x terms or some kind of variable that have exponents on them. One of the things that you need to also remember when identifying a polynomial function is that the exponents must be whole numbers. What does whole numbers mean? Natural numbers, what does that mean? So 1, 2, 3, ... What else? Can you have an exponent of a 0? Is 0 a number we can put into a polynomial? Yes. So that means n has to be greater than or equal to 0, not a decimal or fraction or negative. Okay, so we're dealing with exponents of whole numbers, meaning 0, 1, 2, 3, 4, ... In this expression, x represents our variable. Coefficients are represented by the letter a. The degree of the polynomial is the exponent of greatest power. Okay, another note here. We should always write from, let's say, high to low degree. Okay, we want our highest exponents at the front and then in order down to 0. And our last term that does not have a variable next to it, we call a constant. We can also call it the 0 degree because x to the power 0 equals 1. So I can have like 3 times x to the power 0. This is just going to give me a 3 because x to the power 0 is 1. So it's technically power 0, but we call it a constant because it doesn't really do anything. Okay, so some visual demonstrations of the the first 5 degrees. The first 3 you should be relatively comfortable with. Yes, sir. Sure, I can. The first degree that we're going to talk about is the 0 degree. This is what we call a constant function. Now, I recognize on your printed versions of these workbooks, some of these words are a little bit hard to see. So this is the constant function. Okay, constant means the same number. So if f of x is the same number, no matter what I do, I'm looking at a horizontal line with no slope. No matter what x is, y is always 3. That's why it's called a constant. Constant function is a horizontal line. If I have a linear function, so this word here is linear. Linear function has degree 1. So this is where we have a line equation where we do have a slope. So mx plus b, where slope is not 0. And this looks like, again, a straight line, could be pointing up to the right or down to the left. Degree 2, we call quadratic. This is what you guys did last semester in Pre-Cal 11. This is where we have a highest degree of 2, and it looks like a parabola. The shape of the parabola depends on the equation, if it's shifted, if it's stretched, if it's moved, whatever. But we're focusing on the degree today. X squared gives us a parabola called a quadratic function. Okay, we are going to be comfortable by the end of this semester with any degree polynomial. So this is a cubic function here, means we have a highest degree of 3. So there's an x cubed involved. Could have other degrees in there, like an x and an x squared and a constant, but not necessarily. And we have it going from one end of our graph to the other in both directions. Degree 4, I'm going to write this one underneath here. This is a quartic. Think quarter, 4, or a fourth. Quartic function has a degree 4, and essentially it is like a parabola but has 2 vertices. Not always, but it has essentially a W shape. If it doesn't have any kind of transformations on it, it will also look like a parabola because it won't have any deviation in the middle. But usually the ones we will look at will have essentially a W shape for the quartic functions. And degree 5 we call quintic. That is our degree 5. And this one will look a little bit like a cubic function, but with extra, I've offset this one. An extra peak and valley. Okay. Now that we've seen the first 5 degrees, hopefully you can kind of see some patterns that we can summarize, which we will do on the next page. These facts apply to all odd functions. Okay, so if you have a polynomial that has the highest degree with an odd number, so for example, 1, 3, 5, ... all the odd powers, the shape will always be starting in quadrant 3 and extending up to quadrant 1 if, or when I should say, the leading coefficient is positive. It will follow the graph of a positive mx plus b line going in the positive direction. Okay, the higher the degree, the more squiggles there will be in the middle, but at the end of the graph there will always be a leg going down into quadrant 3 and the other one going up into quadrant 1, up into the right. This is true for all odd graphs with positive leading coefficient. Now, we learned in the last unit that to reflect something over the x-axis, to make it upside down, we multiply everything by a negative. So when the leading coefficient is negative, now it's upside down. Now we have a graph that starts in the second quadrant and goes down to the fourth quadrant. Again, true for all odd function polynomials. The other thing we need to notice is that all of them will have minimum 1 x-intercept, because the range and the domain for odd polynomials is going to be all reals. We can put a cube on anything. So that means it extends down and to the left forever, up and to the right forever. So all reals for the domain and the range. So that means we have to cross a horizontal line at least once at some point. Now, possible that it crosses the x-axis multiple times. So the maximum number of x-intercepts it can have is n, which represents the degree of the polynomial. So if you have a third degree, the maximum number of x-intercepts we can have is 3. Same with 5 and 7 and all the other ones. Always true, the y-intercept is represented by the constant in the equation. So the last term, if it does not have a variable next to it, that will always be your y-intercept. And lastly, because it goes on and on and on forever, there is no max or min because we have a range of all reals. Okay, so this little table here is true for all polynomials that have a degree that is odd. And we'll make a similar chart for all the degrees that are even. So this one is even functions. Okay, even functions will open up starting in quadrant 2, going into quadrant 1. So we're going to be looking for basically W shapes or U shapes. Both of the arms pointing up. If we don't have any squiggles in the middle, it'll be the shape of a U. If we do have some squiggles in the middle, it'll be versions of W's. Okay? Similarly, if we flip it over and upside down and we have a leading coefficient that is negative, now we are looking at essentially things that look like M's upside down. Both arms pointing down from quadrant 2 to quadrant, oh sorry, this is quadrant 3 and 4. This was quadrant 2 and quadrant 1. Okay, so even numbers, both arms go in the same direction, either both up or both down. Up is positive, down is negative. We're looking for the leading coefficient in those equations. Some other facts. It is possible for an even function not to have any intercepts. If you think of the shape, I can take my W and move it up above the x-axis and it's never going to touch it. Or I can take my letter M upside down and move it down below the x-axis and it's never going to cross over it. So it is possible to have 0 x-intercepts. However, the maximum again, n intercepts where n is the degree. So if you have a quadratic, exponent is 2, degree is 2, 2x intercepts. If you have a quartic, exponent is 4, maximum 4 x-intercepts. It could also have 0, 1, 2, 3, or 4. So it's not 0 or 4, but up to 4. 5 minutes. Okay, so then mute. Thank you. Similar as above, the y-intercept is your constant function. Your domain is all reals because we can square everything. What happened? Is the screen not working? Okay. Domain is going to be all reals because we can take any number and multiply it by itself. However, we cannot say anything about the range because the range will depend on the equation we have. If it's positive, then we'll have a minimum. If it's negative, we'll have a maximum. If it's up or down, then the range will change every single time we look at a function, so we can't say anything general about it. But we can say that the domain is all reals. And because we have a distinct shape of W's or M's, then we know that we will always have a maximum or a minimum vertex when dealing with even degree polynomials. Okay, I'm expecting you to know this by heart at some point. By the time the test comes around, we should have this memorized. So in our next example, I've given you 4 equations, and using the rules, I want us to identify, is it a poly? Yes or no? What is the degree? What is the leading coefficient? And what is the constant? Okay, so 4 equations. I'm going to do the first one, or actually, no, sorry, I'm going to do this page with you. I'm going to get you guys to practice on the next page. So, first equation is g of x is 4 to the power x. Is this a polynomial? So I just summarized this statement here. These are the 4 things we're looking for. The 4 equations are here, but I've also rewritten them below. Okay, 4 to the power x is or is not a polynomial? Not. Why is it not a polynomial? The degree is not a constant, right? Remember in our definition, we said our exponents have to be whole numbers. So it cannot be a variable. If this was x to the power 4, that is a polynomial, but this is not. Okay, when you have an exponent that is a variable, this is called an exponential function, which we will learn about soon. The base is a 4, which is a number, right? And the exponent is my variable. So this is not a polynomial, which means I can't answer the rest of the questions. So I'm done and I move on. Look at B. Is or is not a polynomial? It is a polynomial. Okay, what is my leading coefficient? -5, yes. Right? It is the number in front of the highest degree, which is a -5. What is the degree? 3. And the constant? +6. Okay, next one. Y equals x to the power -2 plus 1. Is or is not? Ooh, I heard a mix of answers.
No.
Why not?
It's a negative.
Yes, my exponent is negative, right? Not a polynomial because x to the power -2 is the same as 1 over x squared, right? My definition of polynomials is that my exponents have to be positive numbers and I don't need any variables in the denominator. If you have variables in the denominator, this is a rational function, which we will also get to in the next section. But this is not a polynomial, so I can't answer the rest of the questions. Let's look at this one. Is or is not? Why not? Yes. When we have a radical, this is the same as saying x to the power of 1 over 3. This is not a whole number. This is a fractional number. Right? When we have fractions in the exponents, we end up with a radical function, which is what we did in our last section. Okay, so we're looking for whole numbers and exponents. We want to make sure we're writing them in the correct order. So on this page, this is the one I'm going to do with you. The first one, I'll let you do the rest on your own. I have given you 4 equations and 4 pictures, but they are not matched up correctly. We have to investigate each equation and identify some key features. So look at the first equation here. What is my degree? 3. So this is an odd function. Look at the word bank below. What kind of a function is this? Cubic, thank you. The graph has at least how many intercepts? Minimum. 3 is the maximum. How many minimum? 1 minimum, 3 maximum. The leading coefficient is positive or negative? Positive. So we know that it's going from which quadrant? 3 to 1. Okay, scroll down a little bit here. Since the degree is odd, should this function have a min-max? No. No min or max. How do I find the y-intercept? It's the constant. So look at the function. My y-intercept is at 2. Okay, so a cubic function, y-intercept at 2, and it is positive. Which picture am I looking at? D. So equation A goes with letter D. I want you to take a moment with the people sitting next to you without looking at the picture. I want you to analyze the next 3 equations, answer the questions. Once you have them analyzed, go back to the pictures and match them up.